Suppose given a graph G with 4 vertices and 5 edges, E1, E2, E3 and E4 and E5. Now with respect to this given graph G, I have drawn two trees, T1 and T2. So you can see in T1 some of the edges of the graph G are missing, and also in T2 some of the edges of the given graph G are missing. But T1 and T2 are the spanning tree of the given graph G. So what is chord? It is an edge of a graph which is not in its spanning tree. So with respect to the spanning tree T1, if I want to find out the chords, so what are the chords for spanning tree T1? So it is the edge of a graph which is not in its spanning tree. So we can see in spanning tree T1, edge E4 of a graph is not there. So E4 become a chord. Also edge E3 is not there in the spanning tree. Hence E3 also become a chord. So E4 and E3 becomes chords for spanning tree T1. Similarly, for spanning tree T2, E4 is the edge of a graph which is not present in the spanning tree T2, and hence E4 becomes the chord. Also, edge E5 of the given graph G is not present in spanning tree T2, and hence E5 also becomes the chord. So E4 and E5 becomes the chord for spanning tree T2. Okay. So now, once you know the chords, we'll go for what is a fundamental circuit. Now, what is fundamental circuit is, for each chord there exists a fundamental circuit. Suppose for a spanning tree T1, you have chord, let us say E4. So there exists fundamental circuit with respect to edge E4. Also edge E3, also a chord for spanning tree T1, and hence there exists fundamental circuit for edge E3. So number of fundamental circuit is always equal to number of chords for that spanning tree. So how will you get a fundamental circuit with respect to the edge E4? So if I add the edge E4 in the spanning tree, see now, if I add the edge E4 in the spanning tree T1, so it forms one circuit. So what is that circuit? A, C, D and A. So this becomes a fundamental circuit with respect to the edge E4. Similarly, to find out fundamental circuit with respect to the edge E3, so if you add E3, so how to find fundamental circuit with respect to the edge E3? So add E3 in its spanning tree. So once I add, I should remove this edge E4. So to get fundamental circuit with respect to the edge E3, so you should add edge E3 in its spanning tree. So once you add edge E3, it forms one circuit, A, B, C and A. So this is called as a fundamental circuit with respect to the edge E3. Okay. Now for spanning tree T2, if I want to find out the fundamental circuit, so edge E4 is a chord. So with respect to the edge E4, there exists a fundamental circuit. Also edge E5 is a chord for spanning tree T2, and hence there exists fundamental circuit with respect to the edge E4. So how to get fundamental circuit with respect to the edge E4? Add edge E4 in spanning tree. It forms one circuit, A, B, C, D and A. So this becomes a fundamental circuit with respect to the edge E4. Similarly, to get the fundamental circuit with respect to the edge E5, if I add edge E5 in its spanning tree, again it forms one circuit, A, B, C and A. So now next concept is fundamental cut set. So again consider the graph G. and a spanning tree with this with respect to this graph G. So this graph G contains 4 vertices A, B, C, D, and 4 edges E1, E2, E3, and E4, and accordingly, it's one of the spanning tree of this graph G is drawn. So, how do you get the fundamental cut set for this graph and the spanning tree of the graph? So, fundamental cut set exists for each edge of the spanning tree. So, there exists a fundamental cut set with respect to the edge E1. Also, there exists a fundamental cut set with respect to the edge E3 and fundamental cut set with respect to the edge E4. These are the 3 edges in the spanning tree. So there exists fundamental circuit with respect to each edge of the spanning tree. Now, how to get fundamental cut set with respect to the edge E1? Now, look at this is a little bit tricky. So have a full concentration. So with respect to the edge E1, how do you get fundamental cut set? So if I remove the edge E1, sorry. So if I remove the edge E1, so this breaks the vertices. Okay, fine. If I remove the edge E1 from the spanning tree T, this breaks the vertex set of spanning tree T1 into 2 sets. As you can see, A gets separated and D, B, C get separated. Okay, so same set or same 2 vertex set we should get by removing some edges from the graph G. So to get these 2 vertex set, in where in one vertex set there should be a vertex A and second vertex set D, B, C should be there. So to get these 2 vertex set, which edges of the spanning tree, which edges of the graph G you need to remove. So if you remove the edge E1 and edge E2, so this breaks the vertex set of the graph G into 2 sets A and D, B, C, and this is what we want, and hence edge E1 comma E2 becomes the fundamental cut set for the edge E1. Now, with respect to the edge E3, how do you get the fundamental cut set? So if I remove edge E3 from the spanning tree, this breaks the vertex set of the spanning tree into 2 sets. AD gets separated and BC get separated. Now, which edges of the graph you need to remove to get these 2 vertex set? Which edges of the graph G you need to remove to get these 2 vertex set? If you remove edge E2 and edge E3, so this breaks the vertex set of the graph G into 2 sets, AD and BC, and this is what we want, and hence edge E2 and E3 becomes the fundamental cut set with respect to the edge E3. Now the last one. We need to find fundamental cut set with respect to the edge E4. So if I remove the edge E4, this breaks the vertex set of the graph into two sets, A, D, B, one set, and vertex C as another set. So to get these two vertex set, which edges of the graph I need to remove? So if I remove the edge E4, this breaks the vertex set of the graph into two sets, A, D, B, and C. And this is what we want, and hence edge E4 becomes the fundamental cut set with respect to edge E4. Now let us see one of the very important topic from the tree chapter, that is transport network, where 100% you will find question in the exam again for 5 or 6 or 7 marks question is like Dijkstra shortest path algorithm. Okay, so the question is determine the maximum flow in the given transport network. Now suppose this is one graph which represents one network which is used to carry some material from the node S to node T. So S is called as a source node from where your journey starts, and T is a sink node which is the end node in your network. So you need to carry some material from the source node to the sink node. Each edge is assigned some cost that represent the maximum capacity of that edge. Let us say edge S to B, the cost assigned is 2. So maximum 2 quantity you can carry from edge S to B. Suppose 2 liters of water, right? You want to carry the water, right? So maximum water that you can carry from the edge S to B is 2 liter. So that's how it is. So we need to determine what can be the maximum flow through this network. Okay. So to start with, every edge will be assigned 2 values. One is a capacity that is already given in the problem, and second value we should assign is flow. So initially for every edge we should assign flow value as 0. And edge C to D, let us say, has cost 2. So every edge I have assigned 2 values, capacity and the flow. Okay, so let me correct some values. From edge S to C value is 9, so it is 9, 0. Fine. So as an initial step, I should assign a flow 0 to every edge. Now for every edge there are 2 values, capacity and the flow. Now in next step, what we should do is this transport network uses a labeling procedure to get the maximum flow. Now to proceed with the labeling procedure, you should find out the all possible paths from the source node S to the source node to the sink node T. So what are all possible paths available? Like one path you can say SBT, second path you can say SDT, again SCDT or SBCDT. There are many paths available through which you can carry the material from the source node S to the sink T. So we should explore all these paths and we should find out how we should label this path S, B and T. Now from S you have started. Next you are moving to the node or vertex B. So I should label this vertex B. So how I should label the vertex B is, from which node you came? S. So you should write S plus, comma, the capacity minus flow. So you should write as 2 minus 0. So 2 minus 0 is 2. And hence you label the vertex B as S plus, comma, 2. Now from B, again you will move to the node T, which is your sync node. So you should label this node T. How you should label is, from which node you came? B. So you should write B plus, and the formula is minimum of the previous label of B is 2, comma, the capacity minus flow. This capacity minus flow, that is 2 minus 0. So 2 minus 0 is 2. And hence the final label of vertex T becomes B plus, comma, minimum of 2 comma 2 is 2. So through this path SBT, I got flow value as 2, which I should add in the path SBT. So how I should add is, let us see, S, B and T. Now through the path SBT you got flow value as 2. So I should add this flow value in the path. So S to B 2 comma, initial flow was 0, 0 plus this 2 is 2. Then B to T, the flow value as initially 0. So 2 comma 0 plus 2 is 2. Now you can see both these path S to B and both these edges S to B and B to T got capacity equal to flow. So whenever you get this scenario, like whenever capacity is equal to flow, that you can say the path is blocked. So further you cannot use S to B edge in evaluating the further path. Like next path, suppose you consider as S, B, C, D and T. But you cannot use this path S, B, C, D, T as S to B edge is blocked. Why it is blocked? Because capacity is equal to flow. So that is the point you should remember. Now suppose next path I will consider is SDT. So this will remain as it is 2 comma 2, 2 comma 2, as we got the values in the previous step. So this graph you will keep as it is here. Now we should label this path SDT. So from S you are starting, you are moving to vertex D. So I should label the vertex D. How I should label? From which vertex I came S. So I should write S plus, comma, capacity minus flow. 3 minus 0 is 3. Now from this D you will move to the vertex T. So next vertex I should label, that is T. How I should label? From which vertex I came? D plus, so it's D plus, comma, the formula becomes, once you pass the initial vertex, next time the formula should be the minimum of old label of the vertex D is 3, minimum of 3 comma the capacity minus flow, 5 minus 0, so 5 minus 0 is 5, and hence the final label of T becomes D plus comma just a beta. So minimum of 3 comma 5 becomes 3, and hence 3 is the flow I got through this path SDT, which I should add in the path SDT. So it's 2 comma 2, 2 comma 2. So I should add the flow 3 in the path SDT. So 3 comma 0 plus 3 is 3, and 5 comma 0 plus 3 is 3. So 5 comma 3. Rest values I should keep as it is. Here 9 comma 0, here 7 comma 0, and here 2 comma 0. Okay, so now you can see through path SDT the flow you got as flow value you got as 2. Through this path SDT flow value you got as 3. Will be required these values at the end to calculate final maximum flow. Now next possible path which I can explore, this is C vertex. Now next path which I can explore can be SCDT, because in the path SCDT nowhere you can see the blockage. So although D to T is already been evaluated, but still 2 flow value I can carry through this path, because the flow value currently here is 3 and maximum I can carry is 5. So still 2 quantity I can carry through D to T, and hence I can explore this path S, C, D and T. So third path I can consider as S, C, D and T. So let us label the path SCDT. Here value is 90, here value is 2 comma 0, and here value is 5 comma 3. So from S you came, how I should label the C? S plus comma capacity minus flow. 9 minus 0 is 9. Now from C you are moving to vertex D. So how I should label D? From which vertex you came? C. So C plus comma minimum of the previous flow 9 comma capacity minus flow, that is 2 minus 0, that is 2. And hence final label of D becomes C plus comma minimum of 9 comma 2 is 2. Now from D you are moving to vertex T, which is a sync node, final node. How I should label the vertex T? From which vertex you came? D. So D plus comma minimum of previous label of D, previous vertex label, that is D's label is 2 comma minimum of 2 comma 5 minus 3. This 5 minus 3. 5 minus 3 gives you value as 2. And hence final label of this vertex T becomes D plus comma 2, and hence 2 is the flow I got through this path SC dt, which I should add now. So 9 comma 0 plus 2, it is 2. From C to D, it is 2 comma 0 plus 2 is 2. From D to T, 5 comma 3 plus 2 is 5. And previous values we should keep as it is. Here it was 2 comma 2. Here also it was 2 comma 2. Here 7 comma 0. As it is, we'll keep. So now you can see, to reach the sync node T, there are only two edges through which you can reach to the sync node T, either B to T or D to T. So these two edges anyhow you should have in your any path, but these two paths are already blocked as capacity is equal to flow. So 2 comma 2 here and 5 comma 5 here. So although there exists one more path S, B, C, D and T which are not explored, but we cannot evaluate this path as it is blocked at S to B, and also it is blocked at D to T, and hence we cannot explore this path SBC DT, and hence we should stop here as the path to reach to the sync node T are blocked at B to T and D to T. What is final maximum flow through this network? So through this path SC dt, we got flow value as 2. So what is final maximum flow that we got through this network? So just see the first path which you explored SBT, we got flow value as 2. So 2 plus the second path which you explored is SDT, from where you got flow value as 3. So it is 2 plus 3, and the third path SCDT, we got flow value as 2, and hence your final maximum flow 3 plus 2 plus 2, it is 7.